Friends, in this lecture, in this lesson, we are still stuck to the uniform circular motion, and there are certain more things that I must explain to you about the uniform circular motion. Before I take up examples, I plan to discuss something that I introduced to you and emphasized in the last outing. So, I define angular acceleration. The definition of the angular acceleration is that if angular velocity omega is not a constant like it was in the last lecture, which means that is, we read it as, that is, omega is a function of time t. Then we say that our motion is not a uniform circular motion, but rather a non-uniform circular motion. So, in the non-uniform circular motion, we have angular acceleration, which is explained or defined as time rate of change of angular velocity. It's very simple. It's very simple. So this, which we connote as alpha t, the Greek letter again, alpha, beta, gamma, delta. So alpha as a function of time t, in the limit that the time is infinitesimally small, delta t tends to 0, then this we defined as the omega, the angular velocity at the instant t plus delta t, minus the angular velocity at the time t, divided by t plus delta t minus t, like we have been doing function t2 minus function t1 divided by t2 minus t1. So that way we find that this is delta omega t, okay, the change in the value of the angular velocity divided by this delta t, as this delta t tends to 0 because the limit continues. So this we can define as ddt of omega t. So taking omega t as equal to ddt of theta t, the angular displacement as a function of time t, then we can write this as alpha t as equal to ddt of omega t is equal to ddt of theta t is equal to d2 theta t upon dt square, dt2, and the unit is radians per second. Now this is something that was missing from the discussions that we had the last lecture, and now let us try to learn as to what are the things that we must have for a motion on a general path in a plane. And of course, this plane again we'll take as a horizontal plane, and we say that our motion is along a curved path, which may be circular, which may not be circular. But in the limit that the path is taken as very small, it will have a circular thing because it will have a curvature. Okay? What I said? Curvature. So motion along a curved path, and in that motion both the direction and magnitude of its velocity changes. Okay? The direction changes, also the magnitude changes, or both the things are changing, or any one of them is changing. Okay? And the second point is that the velocity, as we have seen before also in the case of the circular motion, that the velocity is tangential to the path. it makes an angle of 90 degrees. I'm sorry, it is tangential to the path. So if there is a displacement vector, then it makes an angle of 90 degrees with that. A, the acceleration makes some angle. I'll say some angle with the path. It all depends upon which path we are taking and which path we are dealing, etc., etc. So it makes an angle with the path. And the real acceleration A that we had defined earlier, this comprises of two parts, vector AR and vector AT. The sum of the two vectors, okay, where this is AR is the radial component and AT is the tangential component, okay. And we find that the magnitude of this component AT over there, this is equal to dV upon dt, and that of the radial component AR, this is equal to V square upon R, where R is the radius of curvature at that particular instant. So what I said, the term that I have used is the radius of curvature. Now I want to share with you something, that what is the relation between the radius of curvature and curvature. Okay, so curvature is, we'll see, and we can define that the curvature multiplied by the radius of curvature is equal to 1. That means there is an inverse proportionality between the radius of curvature and the curvature. So where the radius of curvature is large, there is hardly any curvature. It's very large, then the curvature becomes equal to very small. And if the curvature is more, so tell me, what is the most curvy thing? What is the most curvy thing? Either on a plane or in 3 dimensions. The most curvy thing is the point, the mathematical concept of point. So point is the most curvy thing, and its radius of curvature, as you know, that this is very, very small, it tends to 0. So as I said, that the magnitude of this tangential component of the acceleration is equal to dv dt, and the radial component is v square upon r. And I explained to you what is curvature and what is radius of curvature. Now we define a couple of things. One is a cap vector, a unit vector tangential to the curvy or whatever circular path, whatever we want to say, that is curvy path, may not be exactly circular in the, but when a small portion of it is taken, then it will appear to be circular with a curvature, etc. And the second vector that we have is r cap, which we define as a unit vector directed radially outward. So here in the definition it is radially outward, but I will show you that it is always radially inward. So if I write the total vector as equal to the sum of the two vectors, like here the radial component and the tangential component, then I write it as dv dt to theta cap, like the value was here, okay, minus, this is minus, and I am emphasizing the minus sign over here, v square upon r cap. This negative sign, the minus, indicates, signifies, impresses itself upon us that the AR is always radially inward on the path that this general motion which you are talking about, the motion or a general path in a plane that exists. So with that, I will come back to what I emphasized on that day in the case of uniform circular motion, that I told you that there is, if this is the vector which indicates my r, then I said that the velocity vector will make an angle of 90 degrees and the acceleration vector will again make an angle of 90 degrees with the velocity vector, so that the two angles sum up to 180 degrees, so that there is a complete opposition between the vector r and a. And this now I am going to introduce to you with the help of what is known as reference circle, something very interesting. So to learn the uniform circular motion a little bit more in detail, and to understand some very beautiful things associated with that, we talk about the reference circle. Okay, the reference circle to show the relations among r cap, v cap and a cap, which I did show to you that my a cap was leading the velocity v cap by 90 degrees, and this in turn was leading this one by 90 degrees, so that we obtain the relation which I reiterate over here. One like this, the other like this, and the third one with the broken line like this. Angle 90 degrees, angle 90 degrees, total angle is 180 degrees between r cap and a cap. R is radially outwards and a is radially inwards. It is towards the center, etc. Now what I have is, I introduce to you the r as a function of t. At time t is equal to 0, I have shown this r to be here, and there is an initial angle which is phi. From time 0 to time t, there elapses an angle here which is theta is proportional to t, so that theta is equal to omega t. This is the relation that I introduced to you, and you by now you remember it by rote. So like y is proportional to x, y is equal to kx, and the constant of the proportionality of this system of motion in horizontal circle that we are talking about, we have been talking about, this is equal to omega t. So the total angle that is there, and which gives the position of the vector r here at time t, the total angle becomes equal to initial angle phi and plus omega t. This initial angle, there is another term that we use, and that is initial phase. So phase or the angle or the argument like I have given over here for the cosine of omega t plus phi and sine of omega t plus phi, the argument of the cosine or the argument of the sine is shown to be, this is basically our angle theta, okay, at that particular moment of time. So now I can write this r as the Rx component, any component along the x-axis at the time t, into I cap plus the y component into j cap where I cap and j cap have been shown as the two perpendicular unit vectors associated with the system. We are taking two dimensions, the thing circle in two dimensions, so that we are able to understand it readily. The magnitude of the vector r has been taken as equal to a, just to distinguish it from capital R or small r or whatever. I'm just taking a vector a. Of course, the magnitude of this, what is the dimension of this? RT. The dimension of RT is in meters. Okay, so and the dimension here as well as the dimension here has to be the same. So because this is a dimensionless quantity and constraint for the system, but this thing is changing, and because cosine of omega t plus phi is a number, sine of omega t plus phi is also a number, omega t plus phi is also a number, being an angle here. So therefore I can write this equation for RT is equal to Rxt I cap plus Ryt j cap, that can be represented like this. Now, as per what you know, I am now differentiating ddt of cos of omega t plus phi, and this is given by us that this is equal to the ddt of cosine, the function is ddt becomes sine of whatever angle is there, so I am writing it sine of omega t plus phi. Next, I multiply with the ddt of the argument, and ddt of the argument, this will become equal to omega plus 0, because phi here is the constant. So I can write this as minus omega sine of omega t plus phi, as also I can write that therefore the ddt of a cos of omega t plus phi, I am just introducing the constant a that was there. Okay, here I have taken that constant a to be equal to 1. So now I am reintroducing this constant, so I can take it out of the differentiation system, and a is here and the next thing is repeated here. So I will get this as equal to minus a omega sine of omega t plus phi. And similarly, after this kind of an exercise, I can write ddt of a sine of omega t plus phi is equal to a omega. Omega comes from the differentiation of the argument here, or the phase. So a omega cos of omega t plus phi. Okay, so these things we can introduce. If we differentiate, then we will get definitely the value of the vector v at time t, defined as dr at time t dt. But before that, I am going to discuss something, and I want to re-emphasize, retell you that the total phase at a time t, this is a function of the time t, capital phi is equal to omega t plus the initial angle or phase, which is equal to, so it becomes equal to omega t plus phi. Okay, I will discuss that in little detail, because I have a different way of doing the differentiation of sine and cosine functions. So I will introduce to you first of all this, the method of differentiation and integration, where I will show that when the differentiation of this function is done, then we get a function which is 90 degrees ahead of it in phase. Okay, so I'll take up this for a very simple relationship as to what is the dd theta of sine theta and dd theta of cos theta. So like I said, I am going to introduce my own way of doing the differentiation of the sine and cosine functions. And I say that instead of the way that we do that dd theta of sine theta, I am just taking theta as a variable, this result I obtain, and all our teachers, they will give you simply this result, dd theta of sine theta is equal to cos theta, and will make us remember that we recall every time dd theta of sine theta is equal to cos theta. Okay, but what I am saying, what I am introducing, and what is the difference between the two of them? I say that dd theta of sine theta is equal to sine theta plus pi by 2. Which means that the phase here is increased by pi by 2 radians. And how we can compare the two phases? It's difficult to compare sine and cosine and say that cos leads the sine by 90 degrees. No. I'll just say that the differentiation, the output of the differentiation of any sine theta or cos theta is sine of theta plus pi by 2, and I'll also show to you, and you can put yourself this dd theta of cos theta is equal to cos theta plus pi by 2. Now, if I expand this by the formula that I gave to you before, and that formula we have to remember, that sine of A plus B is equal to sine A cos B plus cos A sine B. Okay. So, substituting that, I'll get sine of theta cos of pi by 2 plus cos of theta into sine pi by 2. And because cos of pi by 2 is equal to 0, cos of 90 degrees is equal to 0, and sine of 90 degrees is equal to 1. Many times I have iterated that, told you that it is like this. So I get this first term here as sine of theta into 0 plus cos of theta into 1, and this becomes equal to 0, and this becomes equal to cos theta. So I arrive at the generally followed result that dd theta of sine theta is equal to cos theta. But there is a difference. Here what we are doing is, what we can do is that we can compare the phase of this, the angle over here with the angle over here, and the nature of the two functions, sine and sine, is the same. Cosine and cosine is the same. So we can compare the phases of the two, and we can find out that the phase of the quantity that we obtain after differentiation of this sine function is ahead of the phase of the quantity that was differentiated by pi by 2 radians, which is 90 degrees. And this is why here this my velocity vector, which is obtained by differentiating the displacement vector, that turns out to be 90 degrees ahead of it. I'll show it in many other cases, but I've introduced this to you just like that. So if instead of sine theta I take the total value here as a sine of theta, a sine of omega t plus phi, then the differentiation according to my method, and I will say again my method. Okay, this method of course has been lost in the jugglery of mathematics that we have been doing, but I could just borrow from there and find out a very telling thing, that look here, what will happen? A is a constant, and omega comes from the differentiation of omega t plus phi. Okay, the differentiation of argument. So like I did before, a omega sine of omega t plus phi plus pi by 2, which will turn out to be, by the way I have done here, it will be equal to a omega cos of omega t plus phi, which is the general method of doing it. But now we understand that the quantity which I have received, the phase or the argument of this quantity is omega t plus phi by 2, which I am saying that this is equal to phi 2, capital phi 2. This I take as capital phi 1, whatever name you want you can have. And if I subtract this from this, the differentiated output, then we find that the phase phi 2 minus phi 1 is equal to pi by 2. A similar thing we can achieve for ddt of cosine of omega t plus phi. If I have it a cosine of omega t plus phi, I will write by my method, retaining the cosine function here or here also, I'll just write a omega cos of omega t plus phi plus pi by 2, which will be the new phase for that quantity, and which I can write therefore as minus a omega this thing sine of omega t plus phi, whatever. So I don't have to remember, I don't have to rectify, okay, as to how this thing leads that thing, this, that. I have just shown to you that in differentiation, phi 2 minus phi 1 is equal to pi by 2. And I will show that if I do the reverse exercise, okay, that is the exercise of integration of the function, then what happens? I can write, I am writing that integral sine theta d theta, sine theta is dear to us, the students from the yesteryears. These days is the cosine theta, which is darling of the students, the teachers, and this will turn out to be equal to, if we work it out, then keeping this as intact, this will turn out to be equal to theta minus pi by 2. Theta minus pi by 2, okay, plus of course a constant of proportionality. So then the phase of this that we obtain over here is less than the phase of this by an angle of pi by 2 radians. I am just introducing you into the things. Look into the books how the things are done. I am pushing you in the ocean of enjoyment, so that I'll come back to that. If you are not able to understand, no problem, I'll come back to this. I'll come back to this to do it for getting the expression for r cap, v cap, a cap, and seeing that how this phase system it goes. Also, I will show to you by drawing the sine curve. If there are two sine curves which are there, sinusoids, then a question is often asked, and there is a problem with the students, which one leads the other one. This will also I'll discuss maybe in the next lecture, definitely there. And for now, I'm just pushing you into the ocean. Scribble whatever I've introduced over here, it's going to be of lasting value to the students who work out for an hour or so, and they will definitely enjoy how this thing happens, etc. So I have enjoyed, hope you also enjoyed. We meet again.